In the Expanse, they use fusion technology to power their rockets. Now, it's efficient, it produces high thrust, and if you get the right fusion reaction to work, it's barely radioactive, like, at all. But there's a big problem for our sci-fi dreams. Controlled fusion reactions are really hard to achieve. We've spent decades, and will spend decades more, trying to use fusion for energy here on Earth. But fusion isn't the only nuclear reaction available to us. There's also fission. And we already use fission in nuclear power plants and even to power submarines. So why not use it for rockets? We understand the physics, so why are we still launching spacecraft with chemistry? This is a Patreon and YouTube memberships exclusive video to accompany this month's main topic, which is the Expanse's fusion drive. Now, in this video, I'm going to talk about nuclear thermal propulsion, its history, the different types of engines, and most importantly, why we don't currently use it. Thank you very much for being a part of my nerd club, and if you're seeing this video at some point in the distant future, you should think about joining us. Now, the interesting thing about nuclear thermal rockets is that they are not theoretical. They have been built. They've been tested on the ground, and we know that they work. So, what exactly are they? Now, a side note here before we go any further, we are specifically talking about nuclear thermal propulsion, not nuclear explosions. A lot of people were bringing up Project Orion in the comments of the short series, but that is a very different concept that's featured in the three-body problem, and I do have a video all about it, which I'll link here if you want to check it out. A nuclear thermal rocket, on the other hand, it's still a rocket, but one where a nuclear reactor replaces the chemical flame. You have a propellant, something like liquid hydrogen, and you heat it up. The hot gas expands through a nozzle and produces thrust. Now, that basic mechanism is pretty much exactly the same as how a chemical rocket works. The only difference here is where the heat is coming from. Now, in a chemical rocket, the heat comes from a chemical reaction. You burn fuel and oxidizer together, kind of rearrange electrons, and it releases energy. You then use that energy to heat the exhaust. In a nuclear thermal rocket, the heat comes from a nuclear fission reactor. Uranium atoms split inside a controlled reactor core, and that fission releases energy as heat. Liquid hydrogen is pumped through the core, absorbing that heat and expanding into a very hot gas. It's then expelled through a conventional rocket nozzle, and that's basically it. The reactor, it's just a very powerful heater. Its performance depends on how hot you can make the propellant. The hotter the hydrogen, the faster it leaves the nozzle. And the faster it leaves the nozzle, the higher the exhaust velocity. Once you increase exhaust velocity, the rocket equation becomes a bit more forgiving. Now, chemical rockets, they're limited by chemical bond energies. You can only get the combustion chamber so hot before you hit the ceiling of what chemistry allows. A nuclear reactor isn't limited by chemistry, it's limited by materials. So like, how much heat can your fuel elements take? How hot can your structural materials withstand hydrogen flowing through them? The rules of rocketry are basically the same, but the temperature ceiling is higher. And that alone is enough to roughly double the efficiency compared to the best chemical engines. Now, if performance in a nuclear thermal rocket is mostly about temperature, then the entire engineering problem becomes fairly simple to state, but very difficult to solve. The big question, how hot can you make your hydrogen before your reactor destroys itself? Now, hydrogen is the lightest element, which is why it's chosen as the propellant, because light molecules give you higher exhaust velocity for the same temperature. But hydrogen at very high temperature is chemically aggressive. Like it erodes materials, diffuses into metals, and weakens structures. So you're trying to run a nuclear reactor where extremely hot hydrogen is flowing through the core and you need the fuel elements to survive. That constraint is what led to different reactor concepts. Starting with solid core nuclear thermal rockets. Now, this is the most developed design. The nuclear fuel, usually uranium embedded in a graphite matrix, stays solid. The reactor core contains thousands of small channels. Liquid hydrogen flows through those channels, absorbs heat from the fissioning fuel, and exits the nozzle. This is the type that was actually built and ground tested in multiple different countries during the Cold War and beyond. The good thing is that we understand how it works relatively well. It behaves like a very hot, compact reactor with a propellant loop. The limitation is the materials. Because once you approach like a few thousand Kelvin, the fuel elements start to degrade, and that caps your maximum exhaust velocity. So you can improve performance, but you can't like push it arbitrarily high without melting or eroding the core. The next design is liquid core designs. Now, in a liquid core reactor, the nuclear fuel itself is molten. Because it's already liquid, you can run at higher temperatures than a solid structure would tolerate. Higher temperature means higher exhaust velocity and better performance. The problem is containment. You now have liquid fission fuel inside a rocket engine with hydrogen flowing through or around it. Preventing things like mixing or leakage or any instabilities becomes extremely difficult. So the engineering complexity increases pretty dramatically. Now, the last one here is the gas core concepts. In a gas core or nuclear light bulb, the uranium fuel is gaseous or in plasma form. Now, in theory, this allows extremely high temperatures and very high specific impulse. But now you're trying to contain a fissioning plasma with hydrogen flowing around it, separated by radiation transparent barriers or magnetic effects. No gas core engine has ever been built. These are very theoretical. So when we talk about nuclear thermal rockets, we're actually referring to a whole family of designs that all solve the same problem in slightly different ways. And importantly, only the solid core version has ever actually been built and tested at any meaningful scale. So why are we not using them? Solid core nuclear thermal rockets were ground tested. They produced thrust. They achieved significantly higher efficiency than chemical rockets. From a purely technical standpoint, they were viable, absolutely. So why did they never leave the ground? Well, there isn't one single reason. It's actually like a combination of politics, timing, and risk. Firstly, we have that the mission pull disappeared. Like at this moment in time, nuclear thermal propulsion would make the most sense for long duration, high mass missions. So something like a crewed mission to Mars. In the 60s and the 70s, those missions were being seriously discussed. That's the era when most of the testing happened. But once Apollo ended, political focus shifted. Funding went towards the space shuttle and low Earth orbit infrastructure. Mars missions were basically postponed indefinitely. And without a concrete mission that requires nuclear propulsion, the justification just wasn't there. You see, these engines are expensive to develop and it's politically sensitive. If you don't have a mission that really needs them, they're very easy to just cancel, and that's exactly what happened back in the early 70s. Now, the second is the launch risk and the public perception. You see, a nuclear thermal rocket, it's not a nuclear bomb, but it is a nuclear reactor. Now, before startup, the uranium fuel is only mildly radioactive compared to a running reactor. But once the reactor has operated, the core becomes highly radioactive due to fission products and neutron activation. The main concern isn't that it would explode like a weapon. It's not going to do that. The concern is launch failure. If a launch vehicle fails before reaching orbit, which has happened plenty of times, you could disperse nuclear material in the atmosphere or across a crash site. Now, even if the actual radiological hazard is limited, the political consequences would be pretty enormous. Now, there are also international agreements governing nuclear material in space. So the Outer Space Treaty prohibits nuclear weapons in orbit, but it doesn't prohibit reactors. So reactors are technically allowed, but there are UN safety principles and liability conventions that make states responsible for any damage caused by space objects. In other words, flying a nuclear reactor isn't illegal, it's just something you would only do if the benefit clearly outweighed the political and environmental risk. And just for the last however many decades, 40, 60 odd, 70 years of rocketry, that calculation just didn't come out in favor of nuclear rockets. It's not been 7 years of rocketry, it's been over 100 years of rocketry. I take that back. What I meant is like 70 years since we've been sending people up into space, basically. And the last reason is it's better, but it's not revolutionary, right? Nuclear thermal propulsion roughly doubles the specific impulse compared to chemical rockets. That's a really big improvement. Now, it can reduce propellant mass significantly and shorten things like Mars transit times, meaning it can also widen the launch windows. But it doesn't change the propulsion regime. You're still operating within the same basic thermal rocket framework, just at a higher temperature. So from a political standpoint, you're accepting nuclear launch risk for an improvement that, while it's meaningful, isn't like civilization transforming. And it just makes that really hard to justify. So nuclear thermal rockets ended up in a bit of a strange place in history. They showed real proven results, but weren't transformative enough to risk the potential failures. So the question is, where are we now? Nuclear thermal propulsion never went away. It just kind of moved in and out of favor at times. Over the last 15 years, as human Mars missions started being discussed again in serious-ish planning circles, although that's changed recently, hasn't it? Nuclear thermal rockets resurfaced as an option. Logic being simple is that if you want to reduce the crew's exposure to cosmic radiation and microgravity, shortening transit time helps. And nuclear thermal propulsion can reduce travel time compared to purely chemical systems. In the United States, the most visible recent effort was the demonstration rocket for agile cislunar operations, or DRACO. Now, this was a joint NASA-DARPA program intended to fly a nuclear thermal engine in space as a technology demonstrator. The design focused on using high-assay, low-enriched uranium fuel known as HALEU. Specifically using this to avoid the proliferation concerns associated with highly enriched uranium. The idea was to prove that a modern solid-core nuclear thermal engine could be launched safely, activated in orbit, and then operated in space. But as of 2026, very recently, guys, DRACO was cancelled. The stated reasoning was a change in cost-benefit analysis as launch costs dropped and alternative mission architectures became more viable. That's a lot of big words. I'm reading that as they said, hey, we don't want to give it money anymore. The physics didn't fail, but the institutional appetite for it disappeared. But the US isn't the only one who's been looking at this. Russia and the Soviet Union conducted their own research and ground-tested nuclear rocket concepts during the Cold War. Europe has periodically studied nuclear propulsion concepts through ESA-related working groups and research initiatives. And these studies tend to focus heavily on safety cases, like do not activate the reactor near Earth, only start the system once it's in a stable high orbit, or a departure trajectory. Ensure re-entry scenarios are controlled or impossible. But so far, no agency has committed to flying an operational nuclear thermal rocket. The situation today is essentially this. The physics is understood. Solid core designs have been demonstrated on the ground. The engineering challenges are serious, but not like mysterious. The political and environmental risk calculation remains the dominant barrier here. Nuclear thermal propulsion, guys, is not science fiction, and we love when it's not science fiction. It is technically achievable with existing physics and materials science. The question has always been whether it is necessary enough to justify flying it. So nuclear thermal propulsion is in this interesting space. It's technically real, it has been built, it's been tested, it proves that it has the potential to be a really efficient deep space propulsion method. It's not speculative in the way fusion propulsion is. We don't need this major breakthrough to make it possible. But it's also not transformative enough in the way that you might think. It's not going to let us accelerate at 1G for days or drastically reduce travel times across the outer solar system. It can give a meaningful improvement, like roughly doubling the efficiency, which would be significant if we were to be doing manned missions to Mars. The reason we don't use it isn't that it's impossible, it's that it's politically heavy. It's environmentally sensitive. You can only justify this if you have a mission that truly needs it. And right now, we just don't. Now, if you want to build a slightly better version of what we already have, then nuclear thermal propulsion makes sense. If you want to build the world of the Expanse, with ships accelerating for days, flipping and decelerating across the belt, nuclear fission just doesn't give you enough. Nuclear thermal rockets are the bridge between chemistry and something a bit more ambitious. Fusion, it's an entirely new era. Both are really interesting. One is just much closer than the other. But for now, we are still using chemical rockets for launch, and we may always do that, to be honest. Unless we build a space elevator, but like that's for a completely different episode. Thanks for watching, and thank you guys for supporting my channel and letting me make these videos for you. Stay nerdy.